Okay, to start, we have three scenarios that I want to look at, and each of them involves a brick relative to the ground, and I want you to identify what kind of energy it has. Okay, so the first thing, we have this brick that's stationary in the air. Okay, what kind of energy would that have? That would be gravitational potential energy. And we have this one right here that's sliding across the ground. What kind of energy does that one have? Because it has velocity, that means it has kinetic energy. And then we have this one up here that's flying through the air, okay, relative to the ground. Here's the ground. So what kind of energy does this one have? So this one has both kinetic energy and gravitational potential energy. Okay, it has both of them at the same time because it's above the ground and because it's moving too. Okay, and so there are kind of some basic energy types, and now let's kind of talk about analyzing situations. And we're going to really look at situations like this where we have multiple types of energy involved and energy is being transformed. So the first thing we need to understand is that when we look at a system being some object and the other things that it's interacting with, the energy of that system is going to have to stay the same, okay, unless something is changing the energy of that system. But in all the universe, the total energy of the universe has to remain constant. And so it can transform from one kind to another, but the total amount always has to stay the same. And we can use that to our advantage when we're analyzing situations. If we know the energy is the same, we can look at how it was before and after and use that to make some pretty powerful predictions. So the first way we're going to look at this is with this skateboarder, and we're going to use you can see the skateboarder has a pie chart floating above her head, and in it we have green slices and blue slices, and the blue represents potential energy from gravity, the green slices represent kinetic energy. And you can see that those blue slices are biggest at the top of the ramp when she has the most potential energy because she's furthest from the ground, and you can see at the bottom the blue slices are gone because she's at ground level. You can also see at the highest points all the green is gone because at those points where she's turning around, the kinetic energy is gone, there's no more velocity, and you can see that it's all green when it gets to the bottom because that's where she's moving the fastest. Okay, and so what you're seeing here is a transformation between gravitational potential energy and kinetic energy. You can see them transforming back and forth. Okay, and we can use the pie chart to illustrate these transformations, and we'll be doing that in class. Okay, but we can throw there's another thing that we're going to look at here, and this is, sorry, let me take a step back. So there's a transformation going on here, and this is energy that is contained in the system. And so the system is the skateboarder herself because of her kinetic energy, and the second factor in this system is the Earth itself. And we have to include the Earth because she has gravitational potential energy because of her proximity to Earth. If she was in space or nowhere near a planet and there was no gravity, then she wouldn't have gravitational potential energy. And so this exists because the system is Earth. Okay? And so what we'll do now is we'll kind of diagram this just to kind of see how it would look. And we'll also look at those charts real quick. Here I've drawn those energy pie charts for you to look at. We have that interchange between gravitational potential energy and kinetic energy, and then we'll go ahead and define the system as so the system is made up of the skateboarder and the Earth. Okay, and those are our system, those two things, and the energy is being transformed to the skateboarder and then going back to this skateboarder Earth system in the form of gravitational potential energy. There's one other thing I want to mention here, that this is a closed system. So if we were to draw, let's just draw a box around it. So this is a closed system. there's a box around it, which what this means is that all the energy in the system is staying in the system. No energy leaves it. Okay, and one way we can illustrate energy loss is by changing the size of these circles. So if the circles get smaller, that would be energy getting lost. If the circle got bigger, that would be energy being gained. And there's another kind of system we can look at, which is an open system. So if we make this an open system, what that would mean is that energy can be lost. And generally what that means to us is that friction can steal that energy away. So let's go ahead and look at what happens there. So let's make this into an open system. So we're going to restart this. We have the skater right here on the ground. So the first thing I want you to do is observe what happens to the pie chart as she gets moved into the air. Okay, you can see that getting bigger because as her potential energy increases, her total energy increases. Okay, and then as she falls, we can set her here. As she falls, that transforms into the kinetic energy. Okay, but if we enable there to be some friction and make it an open system, then that energy is going to be lost. Okay, so we skate down a little bit, and look, there's a little bit of thermal energy created, and that energy left the system. And so the way this works is it's going to kind of show it the kinetic energy coming out of that kinetic energy slice, okay, over time. And so the way we account for it is that kinetic energy piece is getting smaller, and that energy is leaving the system. So we can show it in that circle as this like shaded off area, or we can just say, well, the circle is going to get smaller, okay, which means there's less energy to go around. And as it goes on, we can say the circle is going to get smaller and smaller, okay. And if we were to watch this over time, eventually she would come to a stop because of that thermal energy leaving the system, okay, and going into basically the environment. Okay, pie chart getting really, really small, okay, until it's all gone. Okay, and so that's energy leaving that system in the form of thermal energy if this was an open system. Okay, so an open system, we could, as you saw there, either diagram it by shading in part of the circle as a different color, or making the circle get smaller and smaller. Those are both options. Okay, and then to wrap up this video, I'm going to show you one other type of chart that we can use to diagram this. So instead of looking at a bar chart, we can look at a bar graph. Okay, and so we're going to be using bar graphs. And so if you look here, we put the skater on the edge, and you can see it switching between potential and kinetic energy. If we allow for there to be friction, then that thermal energy bar is going to keep climbing up, taking from our total energy, okay, and so on. Alright, so when we use the bar graphs in a diagram, we create a chart that we're going to call an LOL chart. So let's make an LOL chart for just one part of this. We're going to compare snapshot A, which we'll call here, and snapshot B, which we'll call here. Okay, and the way that this works is we're going to create bar graphs, and we're going to show the energy transfer using these bar graphs. Okay, so before we do, we're going to say, okay, at the beginning we have gravitational potential energy, and over time when we go from A to B, at position B, all that gravitational potential energy is left at that point, leaving us with kinetic energy. Okay, and now we're going to kind of give a qualitative description here using bars, and we're going to use actually boxes basically. So we're going to say there's some number of boxes here that we started with of energy, and the number that we use is totally arbitrary. It can be as many as you want. The number doesn't matter. What matters is how it changes as you go from here to here. So in this case, the number of boxes of gravitational potential energy is going to go down. Okay, so we draw a down arrow to the point where there's none left at the bottom, at which point all the energy is stored in kinetic energy. Okay, and so kinetic energy, at the end we had 4 boxes, at the beginning we had none, so there was an increase in kinetic energy from 0 all the way to 4 boxes. And again, the number of boxes is arbitrary, doesn't matter, but this allows us to illustrate that transformation. So if we were going to do another chart for this point right here, instead of going from 4 to 4, we would go from 4 for gravitational potential energy to, at the end, it would be split 2 and 2 for gravitational and kinetic at this point right here. Okay, and over time, the boxes are getting moved from here to here, stacked up onto there, and then we get to this side, they're being moved back over. Okay, in the case that it's an open system and there's thermal energy, then what's going to happen is energy is going to leave the system in the form of thermal energy, and it's going to steal away some of these boxes. And once they go to thermal energy, they're gone. And so we'll draw a box right here to represent that energy that's lost. Okay, you can also show it with an arrow coming out of your system, and that's energy leaving in the form of thermal energy. Okay, so the goal of this video was just to have a chance to kind of start working on these charts, and then in class tomorrow we'll start actually using them.